In this video, we consider the properties of an AR1 process with a unit root. Recall that a unit root AR1 process given by yt equal to a constant term plus yt minus 1 plus epsilon t. Now we could find the MA representation. We did that in the previous video. Showed that we could write this as yt given by the initial value y0 plus a linear trend. So these are the accumulated constant terms plus a stochastic trend. So a sum from I equal 1 to t of epsilon I. And we have the usual assumptions. T goes from 1 to capital T. Epsilon t is IID, mean zero, constant variance, sigma squared. And it's independent over time. That's part of the IID assumption. And finally, we assume that the initial value y0 is given. So we will look at the expected value, the variance, the covariance, and the correlation of the process. And in all cases, we condition on the initial value, y0. First, the expected value of yt given y0, we simply plug in. This is the expected value. We use the MA representation of y0 plus delta times t plus the stochastic trend. And we condition on y0. So the conditional expectation of y0 given y0, that's just y0. Then we have the linear trend given by the constant term times t. And then finally note that the expected value of the stochastic trend here, the expected value of each of the epsilons given y0, that's just equal to 0. So this is the expected value of yt given the initial value. So here's a simple plot. We have some initial value y0, and then we note that the expected value simply follows a linear trend with a slope given by the constant term. So what we have here, this is the expected value of yt given y0. It can be increasing or decreasing. That depends on the size of the constant term delta. Next, we look at the variance of yt given the initial value y0. And this is the same as the expected value of yt minus the conditional expectation of yt given y0 squared, and then we condition on y0. Again, we simply plug in using the MA representation and what we got up here. So this is the expected value of yt, which we can write as y0 plus the linear trend plus the stochastic trend. And then minus the expected value, which we found here. So minus y0 minus delta times t. We square this and we condition on y0. Note here that these two terms cancel out. These two terms cancel out. So what we're left with here is the stochastic trend term in here. We square it and we condition on y0. We can write this as the expected value of. And now look at this term here. We have the stochastic trend and we square it. We can rewrite this as the expected value of epsilon 1, epsilon 2, all the way up to epsilon t squared, conditional on y0. Now y0 contains no information about the epsilons, so we can take out the conditional part here and simply look at this as the expected value of y1 squared plus the expected value of epsilon 2 squared plus expected value of epsilon 3 squared plus all the way up to the expected value of epsilon t squared, like this. Finally, we have a lot of cross product terms, but they are all equal to 0 by construction because we are assuming that epsilon t is a white noise process. So all the cross terms here are equal to 0. Note that this is just the variance of the first shock, which is equal to sigma squared. Second term also equal to sigma squared, and so on. We have a constant variance. So what we're left with here is simply t times sigma squared. So that's the variance. And note that the variance here is increasing with t. So it is increasing over time. It is converging to infinity as t goes to infinity. Third, let's look at the covariances. The covariances between yt and yt minus x, and again we condition on the initial value y0. This is equal to the expected value of, then we have first yt minus the conditional expectation of yt given y0 multiplied by yt minus s minus the expected value of yt minus s conditional on y0, and then finally we have to condition on y0 like this. Now for each of these two terms, what we get is an expected value, and here instead of yt minus the expected value, we can simply rewrite this fast using the same trick as up here. This is simply repeating what we have up here. So this is the expected value of the stochastic trend from I = 1 up to t, and we have to multiply that by the similar expression, but instead of t we now have t minus s. So here we get the stochastic trend from I = 1 to t minus s epsilon t minus s like this, conditional on y0. First we have epsilon 1, epsilon 2, all the way up to epsilon t, and in the second sum we have epsilon 1, epsilon 2, all the way up to epsilon t minus s, conditional on y0 like this. So what we get here is the expected value of epsilon 1 squared plus expected value of epsilon 2 squared plus all the way up to the expected value of epsilon t minus s squared, and then we get all the cross products which are equal to 0. Again, the first term here equals sigma squared, same for the second term, and finally we have for expected value of epsilon t minus s like this. So note that now what we get is we get sigma squared, but we don't have t terms, we only have t minus s. So t minus s multiplied by sigma squared, that is the covariance between yt and yt minus x given the initial value y0. Finally, we can use this to consider the autocovariance function rho of s, which is simply the correlation of yt minus s conditional on y0, and that is equal to the covariance of yt minus s conditional on y0 divided by the square root of the variance of yt given y0 multiplied by yt, the variance of yt minus s conditional on y0. What we have to do here is simply plug in. First, the covariance, we have t minus s multiplied by sigma squared, and then we divide through by the square root, and the variance of yt given y0 we have from up here is equal to t times sigma squared. If we look at the second term, we get t minus s multiplied by sigma squared like this. Note now that we have sigma squared multiplied by sigma squared. We take the square root, and then we have sigma squared in the numerator. So the sigma squares cancel out, and all we are left with is t minus s divided by the square root of t times t minus s. And this we can also write as the square root of t minus s divided by t. And note that if we look at what happens as s increases, well, we will see terms in the autocorrelation function which are slowly converging to 0. So there's a lot of persistence here, but they are slowly converging to 0. The number of overlapping epsilons, if we look at yt and yt minus s, decreases as s increases, and therefore the autocorrelation function converges to 0, but it does so very slowly. So that's it for now. Thanks for watching.